Hello everyone, today we're back looking at the Project 65 breadboard computer, and specifically I want to take a look at the SD card interface today, and I want to see if I can speed it up. In the last video I demonstrated loading programs off of the SD card and running them, but it does take a noticeable amount of time to load things, and I think that's something where we can make a lot of improvements pretty simply. So to give you a reminder about how this all works, over here we have a 6522 VIA, which is a sort of standard interface chip for the 6502. It's running at the CPU clock speed of 4 MHz, and it's got two 8-bit parallel ports. And I'm using one of those parallel ports, port A specifically, to communicate with an Atmega 328P microcontroller, which for the rest of this video I'm just going to call an Arduino because I stole it off of one of these boards. The Arduino has an SD card library and a FAT32 file system library, so it can do a lot of the work of reading data off of the SD card. And it's using an SPI, which is a synchronous serial interface to communicate to this little breakout board with the SD card holder built into it. And then you can see I've also got the logic analyzer hooked up and a couple of connections made, so we'll be able to see what's going on that way. But first, let me demonstrate the problem, and then we can take some baseline measurements. So the system is running, and if I run a simple command like ls, it needs to load the program into memory before it can execute it, and that's taking something like 3 seconds. And it has to do that every time before it can actually run the program, which then does even more disk access to read the directory. Now, in order to get a good idea of how fast things are going and so that we can see how much improvement we get with the things we try, I wrote a little speed test utility. And what this does is it will either read or, in this case, write a 10 kilobyte file and measure how long that takes. First, it has to load the actual program, of course. And it says it took us 2.79 seconds to write the file. And then if we read it back, (3.52 seconds to read it back. Now, that's interesting to me, that it takes longer to read than to write. So I want to see why that's happening. And honestly, I'm more concerned right now with the read speed than with the write speed because I'm using that a lot more often. Every time I want to run a program, I have to load it into memory. Whereas with writing, I only do that every so often. So there are a few things I want to try to do today. I know with the parallel port protocol that I wrote that there's a fair amount of redundant information, so we can probably just get rid of some of that data transfer and speed things up quite a bit. But I also want to do some tests and figure out where time is being spent. Is it the 6502 side that is taking most of the time? Is it the Arduino side? And you might think that's lopsided. Now, the 6502 here is running at 4 MHz. The Arduino is running at 16 MHz. But how much faster that really is getting actual work done is not quite as clear. Is it the parallel port interface that is taking a lot of time? Is it the SPI interface to the SD card that is taking all the time? If that's the case, well, I'm not going to dig into that at this point. I don't want to write my own version of an SD library or a FAT32 library. The whole point of using the Arduino was so that I could avoid doing that. But I don't think that'll be necessary. So the neat thing about a project like this is that it's going to give me an opportunity to use the logic analyzer. And few things make me feel like a real hacker the way using a logic analyzer does. For one thing, it's called a logic analyzer. I mean, how cool is that? But the way this will work is that, assuming I've gotten the triggering set up correctly, we can start this up, and then we can run a command and view all the communication that is happening. So let's see what we've got here. Okay, so to explain what we're looking at, in addition to the 8 data lines on the parallel port, there are 2 control lines, which are used for synchronization between the 6522 VIA and the Arduino. The 6502 and the 6522 are in charge of the communication. They're controlling what happens when, and they're using the control line CA2, this top one, to tell the Arduino when it needs to do something. And then the Arduino is using CA1, the other control line, to indicate when it's finished doing something, when it's ready for the CPU to do the next thing, and so on. And just at a very high level, we can see what's going on over the course of several seconds here. So everything started around here when we pressed enter. That's at 0 seconds. And let's see, so the first thing that's happening right up here is that we're sending a command to the SD card telling it that we want to open a file, specifically the executable for ls. And then I think this little spike right here is probably the Arduino sending back its response that the file has opened okay. And then these big thick bars here are what's happening as we send the executable back and forth. And I'm kind of curious about these breaks in it. We'll kind of look at that more closely in a minute. But how many sections are there here? So there are 14 sections here. That's a little bit suspicious to me because I know for a fact that the ls program is something like 7 kilobytes long and change. So I think I might know what's going on there. I think these breaks might be the breaks between individual 512-byte blocks on the FAT32 file system. We'll see if we can figure that out for sure, but I think what's going on is that we're transferring a block here, and then maybe the SD card is reading the next block in during this break here, and then transferring the next one, and so on. And if that's the case, then we know at least that the communication with the SD card is not the bottleneck here. We know that we're taking way longer to send the information back from the Arduino to the 6522. That's my hunch. We'll see if we can figure that out for sure. And then we have this section at the end here. I think that's actually the ls executable running and reading directory entries, because you'll notice it's a bunch of shorter blocks, which would correspond probably to the length of the directory entries. Okay, let's go back to the beginning here and zoom in so we can see the individual transitions here and kind of see what's actually happening. So this first section here is where we're telling the SD card that we want to open up the ls executable file for reading. And the actual contents of the message that we would be sending on the parallel port are, let's see, first there's an ASCII O for open, and then there's 1 byte for the channel number. The channel number is how, in my interface, I've supported having multiple files open at the same time. So there's a control channel that's used for disk operations, and then there are 2 channels that are used to talk to individual open files, so that I can have 2 files open at once, so that I can copy from one to another or something like that. After the channel number, there's 1 byte for the file mode, so read, write, truncate, all that sort of stuff. And then there is the file name, which is 2 characters, ls, plus a null terminator. And then there's a final null terminator for the entire command. So that's a total of 7 characters. You'll notice there's a lot more transitions here than 7, so what's going on with that? Well, that has to do with the protocol, and let's see, and we have 21. So it goes low 21 times, and that makes sense because with the current protocol, to send a byte of data, we're actually sending 3 bytes of information across the parallel port. And that's just with the protocol that I originally devised quite a few years ago. I did sort of a byte-oriented protocol that tried not to use any sort of context or state variables because it was just easier for me to program it that way. So every time we want to send a byte of data across, like the O in the open command, we first send the channel number, and then we send a command, which is either that we want to read a byte or we want to write a byte, and then we send the actual data. So for example, here we would be sending the channel number 0, we would be sending the write command, and then we would be sending the O. And then we would be sending the channel number, write command, the channel number that we want to, of the file that we want to open, channel number, write command, the file mode, 2, 3, this would be the L, the S, and so forth. So there's a lot of redundancy there, and I kind of knew that. I expected that going in. And one of the first things that I think we're going to do is that we don't need to send that much data. One of the simplest things we can do is that we can just combine those first 2 bytes, the channel number and the command, because I'm never going to have more than 16 channels. The Arduino just doesn't have enough RAM to support that many open files at once. And I don't think I'm ever going to have more than 16 commands like that either. Right now, I just have 2. So we could send that data just as a single message, and that would reduce the number of bytes of data that we're sending by 33%. So that would be a significant improvement right across the board. The other thing I'm noticing here, and let's zoom in a little bit more to make it more clear. So yeah, let's take a look in more detail at what's going on with this handshaking between the 6502 and the Arduino side here. So the handshaking has a couple of purposes. First is just data synchronization, so that we give one side a time to read the results before the other side sends the next byte, that sort of thing. The other thing is just bus arbitration. We want to avoid bus contention, which is the idea of both sides of the parallel port trying to write to it at the same time. That can have bad effects, because if one side of the bus is trying to pull it high, while the other side of the bus is trying to pull it low, you've basically created a short circuit. A lot of current can flow across the connection at that point, which can generate heat and which can actually damage the components if it goes on for too long. So we're very careful with the handshaking and with controlling who is or is not trying to write to the bus at any given time to avoid that as much as possible. And I'll also say that it took me quite a while to get this handshaking actually working reliably the way I wanted it to. For a long time I was doing something with just pulsing via CA1 and CA2 signals, and I was occasionally getting weird lockups and things like that. This current version has been very stable for me. It may not be the fastest thing possible, but it works, it's very reliable. And so I don't want to mess with it too much other than just making the whole thing happen a little bit faster. But what's going on here, first off, when the 6502 wants to put a byte onto the parallel port, it will actually tell the 6522 to start writing to the parallel port and set whatever its data value is, and then it will set CA2 low. And that's the signal to the Arduino that it should be reading a byte. But you'll see there's a fair amount of delay here between when that happens and when the Arduino finishes. When the Arduino raises CA1, that tells us that it's finished, and the 6502 will raise CA2 once it's stopped driving the parallel port. And then we wait for the Arduino to acknowledge that and drop CA1 back down to ground before we start sending the next byte of data here. The interesting thing here is that the Arduino is taking a lot more time to respond to things than the 6522 is. So that's something that we can take a look at. The Arduino is running at 4 times the clock speed, but also the software on the Arduino is written in C. It's using the Arduino APIs and just setting individual pins, and I think those APIs have a lot of error checking and so forth, so they're probably not tremendously fast. Whereas the software on the CPU side, the 6502 and the 6522, is all written in assembly, and it's able to change things on the entire parallel port with just a single instruction. So that tells us that if we're looking at optimizations, well, now I've looked at the 6502 code, and I know that there are at least a few bytes that we can trim off of those instructions, but it looks like if we want to make some real differences, we're also going to have to look at the Arduino side code and see if we could speed that up a bit. So all this we've learned just from looking at the command that is telling the Arduino to open the ls executable file for reading. But let's go a little bit further. So after that, the 6502 sets CA2 low again because it's trying to send a command to read a byte. It wants to read the status, the result of this attempt to open. But that's not going to happen until the Arduino actually finishes opening the file, which takes a few milliseconds. So here we're sending back the file status, which is just going to be a single byte, and then the CPU is immediately going to start trying to read bytes of data. And that, again, takes a while before it gets to the first bits of data here. So I think here is the end of the request for the first byte, and then we have the second byte. We send the channel number, we send the read command, and then we read the data. What's interesting here is that every third one, the reads are taking individually longer than the writes. Because here the 6522 is writing a byte. Here the 6522 is writing a byte. Here the 6522 is reading a byte, and the Arduino is writing a byte, the actual data byte of the program. And all through here, every third data byte where the Arduino is actually driving the bus takes longer than the cycles where the 6522 is driving the bus. Now, I'm not positive here, but I think that might kind of confirm what I'm thinking about the code on the Arduino side being comparatively slower than the code on the 6502 side. Because inside this block, between where this goes low and this goes high, the Arduino has to change the pin modes for all of the pins on the parallel bus so it can write to them. And it's doing those individually with just the pin mode call in the Arduino API. And then it has to set the value, and then it has to set them all back to read mode at the end in here. So that looks like another opportunity for some optimization. So yeah, just a lot of data all being sent one byte at a time, and each byte actually taking 3 transfers on the parallel port. So we'll definitely need to fix that. Here's the first of those spaces between sections of data that we're reading. And yeah, I suspect this is probably where the Arduino is reading data from the SD card. So typically in a FAT32 file system, blocks can be 512 bytes, and I think that's what's happening here. But maybe if we play around with the timing, we can determine that for sure. Do I remember how to add measurements? Let's try this. And we'll just do this approximately. 174 milliseconds. Okay. And then if we zoom in here and do another measurement, let's do 4 bytes of data transfer, just so any amounts of error will sort of average out. 1.36 milliseconds. Now if we take 174.5 divided by 1.36, is 128, and that was across 4 bytes. So yeah, that's 512 bytes of data that are being sent across between the start of this section and the end of it here. So each one of these blocks is sending 512 bytes, and the ls command is, yeah, about 7K, so 14 of these blocks makes perfect sense. This is what I love about using the logic analyzer. You can see things actually happening, how long they take, what's going on. It's the ground truth of what's happening inside the computer. It's just really cool. Okay, so let's try to make the absolute simplest change first. And that's going to be changing our protocol. Let's see if I can find the right spot here. Change our protocol so we're not sending quite so many bytes on the wire just to send a single byte of actual data. So this is the code for get characters. So this is the 6502 trying to read a byte. And here we see it sends the device channel and the read a byte command, and then it actually reads a byte from the parallel port from the Arduino. So we can combine these two easily enough. We're just going to send a single byte. The device channel will be the lower nibble of that byte, and the command will be the high nibble. So we'll have to come up with a different number for this command. We'll just start here, and we will add, let's call it 10 for when the 6502 wants to read. Then we'll send a single byte and comment these two out. And then down here, this is how we write a byte to the Arduino, and basically the same thing. Device channel will be the low nibble, which it already fills. 20. Comment that out, comment that out. So now we're only sending 2 bytes to send 1 byte of real data, which is still 1 byte too many, but we have to start somewhere. Oh, I lie, there's one other place we need to change. In addition to reading a byte and writing a byte, there's also the seek command that uses this same structure, so we'll need to change that. Open and close should be fine, but seek. And I'm just ORing these values together, so I guess this will be 30. And comment that. So that should be all the changes that we actually have to make in the code here on the P65 side. Now we just have to build and send the data across. I have to turn on the P65 and update the ROM, which I can actually do in place with this handy little program. So this is doing an X modem transfer of the new ROM image. And then I have to flip my write protect on my EEPROM. And update it all in place. I might speed this up for the video. Okay. And reboot. Well, at least we haven't bricked ourselves, we know that much. Now we have to make the corresponding changes on the Arduino side. Here we go. And I think the code I want is down here towards the bottom. Yeah, where we're reading the channel and the command. So instead, we're going to read 1 byte. There we go. That's what I mean. Channel in the low nibble. Command in the high nibble. Except that we also changed the actual numbers that we're using for the command. So let's see. For seek, we just said that is 30. 6502 wants to read a byte. That was 10, I think. And 6502 wants to write a byte is 20. Okay. Right. Oh, what did I do? Really? That's silly. Okay. All right, the EEPROM in the 6502 side I could update in place. With the Arduino, I don't really have an easy way to do that right now, so I'm doing this the hard way. I've written it onto a separate Arduino, and I'm just going to swap the chips. We better turn off the power, use the chip puller. I should probably turn on some more lights. Now, it is probably possible for me to find a way to do that update in place. It's a little tricky because I'm using every single digital pin on the Arduino for one or another of these purposes. And when you're doing some manual intervention like this, there's always the chance of screwing up and putting a chip in backwards or something like that. But I think that's right. And we will find out. Okay, does it work at all? It still works. That's good. Now let's see what's happened to our disk speeds. .95 seconds for the write test. Now I've been keeping some statistics in a file here. Now I did a bunch of runs just so we could see how consistent they were, and they were very consistent, just off by 1/10 of a second one way or another. And 1/10 of a second, or sorry, 100th of a second rather, is the resolution of my interrupt-based clock. Although I did see one bit of weirdness. When I was recording the intro earlier today, I got 2.79 seconds for the write test. And then when I went back and did 10 runs, I got 2.72, 2.73, 2.74. But in any case, 1.95 is a nice reduction in the time. And in the read test, what do we get? 2.73. So down about 0.7 of a second. That's not too bad. In fact, let's think about this. Okay, so for the write case, we've got about a 40% speed up. And for the read case, it's not going to be quite that good, but divided by 2.73, yeah, 29% speed up. So that's a pretty good start, and it didn't require us to do anything really complicated yet. Okay, one more thing for tonight. It's New Year's Eve. I have some mildly alcoholic eggnog here, and that makes it seem like a good time to try to optimize a little bit of assembly. I don't think this will make a huge difference performance-wise, but why not? When I was looking at this code earlier, I saw a few things that I might want to change. So this is the code that we were just editing, SD getC and SD putC. And they do the whole protocol for sending or receiving a byte of data from the Arduino. But they use these routines, write byte and read byte, that just do the actual wire protocol of the parallel port. And that stuff is up here a little bit. And I noticed when I was looking at these that there are a few things that we could get rid of some instructions. And these are also interesting bits of code because they're doing all the actual communication and setting registers in the 6522. And if you look at this write byte, for example, well, first off, there's 3 no-op instructions at the end of it that I think we can safely comment out. I think these are leftovers from some previous debugging session, so we can get rid of those. That's like 6 clock cycles, so 1.5 microseconds. That's a huge optimization. Really, it is. So if you look at this here, when we're writing to the parallel port, the first thing we do is set this is called the data direction register for port A of the VIA. And we set it to say that we're writing. We want to avoid bus contention, so both sides of the parallel port we keep in read mode as much as possible. And we only switch over to write mode when we have to, like right now. So we set the data direction register, and then we set the actual value on those lines with the value in the A register. And then we have to mess with our CA2 and CA1 control lines. Now remember, the 6502 side uses CA2 to signal to the Arduino side when something is going to happen. And then the Arduino side will use CA1 to notify back to us that it's done whatever it needs to do. For example, in this case, that it will have read the value that we put on the parallel port. And we set CA2 by writing particular values to the peripheral control register. I think that's what PCR stands for. And that's one 8-bit register that controls both port A and port B, so CA2, CA1, CB2, and CB1. The CA2 line that we're using to send control signals to the Arduino, we can set directly. We can set it low here, we can set it high down here. CA1 we can't actually check directly. Instead, we have to set the control register to say whether we're interested in, for example, seeing a positive edge or a negative edge. And instead of reading the value directly, what this does is that when the event that we're asking for, like a positive edge on CA1 happens, it'll set a bit in a different register. So I have a macro here where after we've set CA2 low, we do this wait CA1 to wait for CA1 to change, to wait for that signal from the Arduino. And wait CA1 is right up here, and in this case we're reading IFR, interrupt flag register. That's what it is. And the bit that we're interested in that tells us if the event that we're waiting for on CA1 has happened is bit 1, starting from 0. So we're going to AND this with a 2, and just do a hard loop polling until we get the signal that we want. Now the reason that this is in the interrupt flags register is that you could also set up an interrupt to signal you when this happens. We don't really need to do that in this case. We can just do this entirely in a polling way and it'll be simpler. But I did also notice that when we exit from this wait loop, I load a 2 in here so that I can write back into the interrupt flag register. What this does is that it clears the flag register so that we can do another wait later on. But it occurs to me that there's already this value 02 in the A register because of all this stuff here. So we should be able to comment that instruction out too. So it's a couple more clock cycles. So going back to write byte, we do that wait for CA1. When this wait finishes, we know that the Arduino side has read the byte that we sent to it. Then we set the data direction register back to read mode, and then we wait for the negative edge trigger on the CA1. Basically, we're waiting for CA1 to acknowledge that we've gone back into read mode and it's safe to continue. Now, I have a PHA and PLA here. And I think this must have been left over from copying this from like readbyte, where it would actually be useful. I don't need to preserve the value in the A register here, so those can both go away also. And I think this code should now have exactly the same effect as the original version. It's a few instructions shorter. Is that going to make much of a difference? In a single byte, I don't think so. But in our test program, we're going to be sending 10 kilobytes of data. That'll add up a little bit, hopefully. And down here in readbyte, we have some of the same things. We're using wait CA1 again, so that should have the same effect of having removed that one instruction. We have the 3 no ops that we can get rid of. Now in this case, readbyte actually does have to return the value that it's reading from the parallel port. But it occurs to me that we might be able to speed this up a little bit still. So instead of putting this value in A, let's put it in X instead. And let's use the A register here for setting the peripheral control register. And then we don't need to push A onto the stack here. And here we just need to copy the value from the X register where we've stashed it into the A register. So again, that saves us maybe another 4 clock cycles. All right, let's try that out and see if it still works. The nice thing about making changes inside the SD card reader code is that I generally don't have to worry too much about accidentally screwing up and bricking the system. Even if I break the SD reader, I should still be able to download a fresh copy of the in situ EEPROM writer program and write a new image and hopefully fix myself. Okay, does the interface still work? Looks like it. We'll do the write test first. And just so we remember, here's some tests from the last run. 1.92. So that's a little bit of a change. It's measurable. And for the read test, 2.74. Ah, no noticeable difference. That's a disappointment. Well, anyway, it was worth a try. But clearly, if we want to get a significant performance boost, we're going to have to do something smarter than just bumming a few instructions. So it's been a couple days and I've had a chance to edit some of the earlier footage and write a little bit more code. We've tried a couple things so far. We've worked on the protocol and that gave us quite a bit of speed up. We also tried bumming some instructions from the assembly language code on the 6502 side, and that really did not make much difference. So let's go back to working on the protocol. The current communications protocol with the SD card is character-oriented, and we've gotten to the point where we can send a command and read a byte. So the next logical step is to send a command and read a whole bunch of bytes. For example, read the entire 10 kilobytes of the test data that we're using for the performance test. And that's the code that I have open here. This is the C language program that I've been running to get performance timings. And the actual work here is being done on this line, which is just calling the Unix-style read function that I created when I was getting the CC65 C library set up for the Project 65 computer earlier this year. Well, actually last year now, I guess. So if we look at the implementation of that in the C library, so this function is fairly long. It's not really conceptually complicated. It's just finicky because it's dealing with 16-bit numbers. The count of characters that we want to read and the indices into the buffer are 16-bit numbers, so anytime we operate on them, we need to use several instructions. And that just makes this function a little bit longer than it might be otherwise. Really, all that's going on here is that we're taking the file descriptor that we passed to it, we're mapping that to one of my kernel's device numbers, and then we're going into a loop where we're calling this p65 dev getC. And this is part of the generic device interface in the p65 kernel. This JSR will get mapped to something that is device driver specific, like the SD getC that we were looking at a little while ago. But in order to do a more efficient protocol, I've had to replace this version of the read function with a new version that pushes more of the work into the operating system level. So this version, you'll see, does not have any loop in it at all. And instead of calling p65 dev getC, it calls p65 dev read. So this is a new routine that takes a number of characters to read instead of just reading one character from the device. And all the rest of the code in this routine is really just taking the arguments that get passed from CC65 and putting them into a location and a format where the operating system can get to them easily, and then returning the results or the error codes as case may be. But all the real work is being done by the call to p65 dev read. So going back to the OS code, let's see. This is the device table inside the OS that lists all of the individual devices and maps each of them to the particular device driver calls. And so what I've done is I've added at the end here SD read for the 3 channels of the SD card, and default read is just sort of a generic version that I can use in these other devices like the serial device. And default read is basically just doing the same thing as that original version of the C library read. So using default read would not give you any performance benefit, but using this new SD read, we have the option to change the protocol that we're using to talk to the SD card to do something a little more efficient. And we can find that over here in the SD card driver. So here's the SD getC function that we were looking at a little while ago. And then down at the bottom here, we have SD read. And again, this has a little bit of the finickiness of the original read because it's taking a 16-bit count and has to operate on a bunch of 16-bit numbers. But mostly it's just doing a loop where it's reading characters. But there are a couple of changes. The first thing is that we only send a command once at the beginning of the read operation, and the command is going to be 3 bytes of data. So it's going to be a command value, which is going to be 40 hex, and then we'll send 2 bytes that are just the count, the number of characters that we want to read. After that, we're going to go into a tight loop where we're just going to call read byte over and over again until we've got to the end of the count. Read byte, of course, is the function that just transmits a single byte of data from the Arduino to the 6502 and doesn't do any of the other protocol stuff. So if we do this, then we send 3 bytes here, and then we read count number of bytes here. Now, there are a few special cases that can happen, like if we hit end of file earlier than we're expecting, or if an error happens. So I've set up a system of escape codes to deal with that. If the byte we read is hexadecimal 1B, that's the escape character in ASCII, we know that it's an escape code, so we read a second byte of data. So escape 0 means that there's no character available from the device yet. Escape FF means we've hit end of file. Escape E means that we've encountered an error code. And escape is just an escape character. So once in a while we'll have to send 2 bytes of data, but most of the time we'll just send 1 byte of data to read 1 single byte. And then all of the rest of this code is basically just return codes and error handling and stuff like that. And we also have to implement our new command on the Arduino side. So here we've just added a handler for our new command number 40 hex, and that will go up to this routine read right here. And setting aside the error handling, this is pretty straightforward. We just read the next 2 bytes, which are the count of the number of bytes that we want to send to the 6502. And then we go into a loop where we read from the SD card and write out to the parallel port. And then we have a little bit of extra checking in here for those escape code sequences that we might need to send under certain circumstances. So that's all there is on this side. It's pretty simple. And I've updated the ROM and the Arduino, so let's fire up the P65. Find my copy of TerraTerm here, and do a couple more disk speed tests. Now we haven't done any additional changes to the write speed, so this should stay pretty much the same as what it was in our previous test runs. 1.92 seconds. Okay. But for the read test, we should hopefully see a noticeable improvement. 1.78 seconds. So now that's even faster than the write version. So let's see. Just to compare, so after our attempt at bumping instructions, we were at 2.74 seconds for the read. We're now at 1.78, so we've cut off almost another second. And since we started at about 3.53, we're almost double what we started at. In fact, let's see. A 98% speed up. That's not too bad at all. Let's take a quick look over in the logic analyzer. And once again, I'm just going to start this up and do an ls just to see the program load, which should also be already using the new read routine. So again, this first part where we're writing the instruction, that should not have changed at all because we haven't done anything with our writes. Over here in the read, you'll notice that these first couple look like what we were seeing before, where we have a command and then a read, a command and then a read. The first 2 bytes of a file in the P65 tell us where in memory we should be loading it into. So until we read those, we don't have a memory buffer location to pass to the read routine. So those 2 bytes we just read individually, and that happens here and here. And then these 3 transitions here are where we're sending the write command, which is 3 characters, the 40 command, and then 2 bytes of the size of data that we want to send. And then we just have the longer transitions where the Arduino is writing a byte to the parallel port. So that's a pretty good improvement here. We've pretty much doubled our speed already. I do think there's a lot more that we can do. Going in here at close up, there's still the problem that when the 6502 asks for a character here, it takes a long time for the Arduino to respond. And when the 6502 says it's done, again, it takes a long time for the Arduino to say that it's ready for the next byte. So I think this video is getting long enough, and this is a good time to break it up into a couple of parts. So in part 2, I think what we'll start out with is doing a deeper dive into the code on the Arduino side of this and seeing if we can speed up, probably starting with the pin handling, and just see if we can make that all go a bit faster and get these times for sending individual characters down. Because it looks like that's where our opportunity to make the biggest speed improvement is now. So hopefully I'll get part 2 out pretty soon, and then we will see what happens.